Hello, ladies and gentlemen. This is video number 2 in a two-part series on improper integrals. In our last video, we took a look at two different improper integrals. One of them was convergent, meaning there was a numeric value for the definite integral, and the other one was divergent. The limit of the integral did not exist. They were both considered improper integrals because the only way to really evaluate them is to think about them in terms of limits, and that one of the bounds of the interval tends towards a particular value, either tends towards infinity or tends towards a particular value. In both of these integrals, the right bound of the integral went towards infinity. We're going to take a look at some other examples of improper integrals. The first example here is going to be 1 over 1 plus x squared. Let's take a look at the graph. Before we consider any sort of improper integral, let's try out a fairly straightforward definite integral, just a regular, definite, proper integral, the one that will give us this area under the graph. We can represent this area under the graph with this integral from 0 to 1 of f of x. This is not an improper definite integral, and we will not require any sort of limit to think about this area. To evaluate this definite integral, we need to take the antiderivative of 1 over 1 plus x squared. Before you start launching into some sort of u substitution or some sort of integration by parts, please keep in mind that that is in fact the antiderivative of arctan, or inverse tan. When we apply the first fundamental theorem of calculus, we can evaluate the integral. So now let's step it up a notch and consider an improper integral. This one is going to be similar to the ones we were presented with in the first video. We're going to have a right bound that extends to infinity. We can represent this definite integral like this, from 0 to infinity of f of x, but we will have a better time thinking about this if we think about it in terms of limits. Instead of from 0 to infinity, we're going to go from 0 to b, as b tends towards infinity. Now we are talking about improper integrals. The approach for evaluating this improper integral, though, is not very far off from the definite integral, the proper one, from before. Let's take a look here. It's the same antiderivative, and if we apply the fundamental theorem of calculus, we end up with arctan b minus arctan 0, and here you might need a little guidance. Arctan infinity. What the heck is arctan of infinity? Arctan 0 is 0, so that part's a piece of cake. But let's take a closer look at arctan infinity. Let's go back to, perhaps this is something you talked about in pre-calculus or earlier in this calculus year. The arctangent function is the inverse of a tan function, the tangent function. However, it's a tangent function with a restricted domain from negative pi over 2 to pi over 2. We restrict the domain of the tangent function so that it passes the horizontal line test, so that it becomes a one-to-one function. When it becomes a one-to-one function, we can consider its inverse, which is arctan. The graph of arctan is going to be similar, except the domain and the range are going to be swapped. The domain of tangent x was from negative pi over 2 to pi over 2, and the range was from negative infinity to positive infinity. With the inverse, the domains and the ranges are swapped. We our range is only from negative pi over 2 to pi over 2, and the domain is all real numbers. If we take a look at this bottom graph, then we can see that as x tends towards infinity, the graph gets closer and closer to the horizontal asymptote at pi over 2. Therefore, arctan of infinity is just pi over 2. So let's go back to the problem with this little nugget of information. The final result then, the area under the graph of f of x is pi over 2. The original limit, then, the limit of the integral exists. So this integral, this improper integral, is convergent. Now, let's take a look at the other side of the graph. In the first one, we took a look at the interval from 0 to infinity. And now, how about negative infinity to 0? Same graph. We represent the area under the graph with this integral from negative infinity to 0. And we can think of it as a limit as a approaches negative infinity over the interval a to 0. Now, another topic from pre-calculus was the idea of symmetry of functions, symmetry over the x-axis, symmetry over the y-axis. This particular function has symmetry over the y-axis. So the area on the left side of the y-axis can be expected to be equal to the area on the right side of the axis. Another way of saying this is that f of x is an even function, and that f of x is equal to f of negative x for all values of x. These three things all say the same thing. This little fact saves us a lot of time because this limit, this integral, is going to be equal to the first one we took a look at, which was pi over 2. The reason we bring this up now is that we can take a look at the entire graph, the area under the whole thing, from negative infinity to positive infinity. One way we can go about evaluating an integral like this is by splitting it into two different integrals, one from negative infinity to 0 and one from 0 to infinity. Both of those gave us the same area of pi over 2, so the total area under the entire graph is just pi. And it turns out that from negative infinity to infinity, f of x, the integral, is a convergent improper integral. And it's a little different than the first ones that we took a look at, because the left bound of the interval tends towards negative infinity, and the right bound, both bounds tend towards in opposite direction. So let's give you an opportunity to practice one of these guys. We're going to consider the function f of x equals 1 over the square root of x. We're going to take a look at its graph right here. And we're going to consider this definite integral. This is not going to be an improper integral. This is simply going to be the integral, the definite integral from 1 to 9. So if you would pause the video at this time and try to find an answer. Well, let's see how you did here. Feel free to pause the video again to work through the steps. We are going to expand on this, though, by thinking about this in terms of an improper integral. The way we can do this is to generalize the left bound. Instead of from 1 to 9, we are going to evaluate this from a to 9. So let's pause the video again. Just give me the setup. I'd like to have you set up this definite integral. Okay, so hopefully you have a result that's very similar to what we did. The process is very similar to what we did when we evaluated the integral from 1 to 9. We find an antiderivative, and we apply the fundamental theorem of calculus, and we get 6 minus 2 times the square root of a. That means the definite integral from 7 to 9 is going to be 6 minus 2 times the square root of 7. The definite integral from 0.01 to 9 is going to be 6 minus 2 times the square root of 0.01. This leads us to another example of an improper integral. This time we sort of move to the left towards 0, and we accumulate area under the graph as we get closer to a vertical asymptote at x equals 0. F of 0 is undefined because it will cause division by 0, and this in turn causes a vertical asymptote at 0. The question is this a convergent or divergent improper fraction? If we keep inching closer and closer to 0, does the area under the graph converge towards a number, or does it just keep expanding without bound towards infinity? Once we have it set up like a limit, we can evaluate the integral using the fundamental theorem of calculus. The limit as a approaches 0 from the right. That little plus sign means we're approaching from the right. We have to specify that, though, because we cannot approach 0 from the left in this problem. The function doesn't exist to the left of 0 because we'll end up with the square root of a negative number. There is no real solution to that. So we must specify that we are approaching 0 from the right. And 2 times the square root of 0 is just going to get you 0. So this does converge to 6. The integral is a convergent improper integral. We'll take a look at 2 more problems. Each of them are based on this function. F of x is equal to x minus 2 to the power negative 2/3. This graph looks like this. As you can see, we have another vertical asymptote on our hands. And we are going to evaluate an integral that considers the area under the graph bounded by that vertical asymptote. So why don't you give this a shot? Let's see if you can start setting it up. I'll give you the first step here. This first step actually shows why there's a vertical asymptote at 2. The negative 2/3 exponent causes the x minus 2 to go to the denominator, and you can see now in the denominator x equals 2 is going to cause some problems. So it does lead to a vertical asymptote. So take a moment and see if you can evaluate this integral and determine whether it is divergent or convergent. Let's see how you did. First step, consider it as a limit. It's important to specify that we're approaching 2 from the left. We find the antiderivative, apply the fundamental theorem of calculus, and consider what happens to that expression as b approaches 2. Sure enough, this is a convergent improper integral that converges to 3. The last problem we will consider is an integral that has a vertical asymptote within the bounds. Between the left bound at 1 and the right bound at 4, there is a vertical asymptote. So we're going to evaluate this one in a similar way we evaluated the first problem, and that was by splitting it into 2 separate integrals. The integral from 1 to 4 can be found by evaluating the integral from 1 to 2, evaluating from 2 to 4, and adding the results together. We already know the answer from 1 to 2. That was equal to 3. We think about both of these in terms of limits. The first one we're approaching 2 from the left, and the second one we're approaching 2 from the right. The variables for the first integral, the variable b in the first integral represents the right side of the bound, and the variable a in the second integral represents the left side bound. We only need to evaluate the second integral since we're finished with the first. The process is going to be very similar. Find the antiderivative, apply the fundamental theorem of calculus, and we end up with 3 times the third root of 2. Add them together, and we have the total area under the graph from 1 to 4. 3 plus 3 cube root of 2. This then is another example of an improper convergent integral. It converges to 3 plus 3 times the cubed root of 2. So it turned out that all of the examples in this little video were all convergent. If you get a numeric answer at the end of your problem, then you are dealing with a convergent improper integral. If after considering a limit, you end up with a limit that does not exist, something might tend towards infinity, then what you're dealing with is a divergent integral. So I hope you have enjoyed working through these examples as much as I have had sharing them, and that they guide you through problems of your own. Goodbye.